Let me share with you today an original discovery, but I want to tell it to you the way it really happened, not the way that I present it in a scientific meeting or the way you'd read it in a scientific paper. It's a story about beyond biomimetics to something I'm calling biomutualism. I define that as an association between biology and another discipline where each discipline reciprocally advances the other, but where the collective discoveries that emerge are beyond any single field. Now, in terms of biomimetics, as human technologies take on more of the characteristics of nature, nature becomes a much more useful teacher. Engineering can be inspired by biology by using its principles and analogies when they're advantageous, but then integrating that with the best human engineering ultimately to make something actually better than nature. Now, being a biologist, I was very curious about this. These are gecko toes, and we wondered how they use these bizarre toes to climb up a wall so quickly. We discovered it, and what we found was that they have leaf-like structures on their toes with millions of tiny hairs that look like a rug, and each of those hairs has the worst case of split ends possible, about 100 to 1,000 split ends that are nano-sized, and an individual has 2 billion of these nano-sized split ends. They don't stick by Velcro or suction or glue, they actually stick by intermolecular forces alone, van der Waals forces. And I'm really pleased to report to you today that the first synthetic self-cleaning dry adhesive has been made. From the simplest version in nature, one branch, my engineering collaborator Ron Fearing at Berkeley has made the first synthetic version. And so has my other incredible collaborator, Mark Kutkowski at Stanford. He made much larger hairs than the gecko, but used the same general principles. And here's its first test. That's Keller Otta, my former PhD student, professor now at Lewis and Clark, literally giving his firstborn child up for this test. More recently, this happened.
This is the first time someone's actually climbed with it.
Lynn Verinsky, a professional climber who appeared to be brimming with confidence.
Honestly, it's going to be perfectly safe. It'll be perfectly safe.
How do you know?
Because of liability insurance.
With a mattress below and attached to a safety rope, Lynn began her 60-foot ascent. Lynn made it to the top in a perfect pairing of Hollywood and science.
So you're the first human being to officially emulate a gecko.
Wow, and what a privilege that has been.
That's what she did on rough surfaces, but she actually used these on smooth surfaces, 2 of them to climb up and pull herself up. And you can try this in the lobby and look at the gecko-inspired material. Now, the problem with the robots doing this is that they can't get unstuck with the material. This is the gecko solution. They actually peel their toes away from the surface at high rates as they run up the wall. Well, I'm really excited today to show you the newest version of a robot, StickyBot, using a new hierarchical dry adhesive. Here's the actual robot. And here's what it does. And if you look, you can see that it uses the toe peeling, just like the gecko does. And if you could show some of the video, you can see it climbing up the wall. There it is. And now I can go on other surfaces because of the new adhesive that the Stanford group was able to do in designing this incredible robot. Oh, one thing I want to point out is look at StickyBot. You see something on it. It's not just to look like a gecko. It has a tail. And just when you think you figured out nature, this kind of thing happens. The engineers told us for the climbing robots that if they don't have a tail, they fall off the wall. So what they did was they asked us an important question. They said was, well, it kind of looks like a tail, even though we put a passive bar there. Do animals use their tails when they climb up walls? What they were doing is returning the favor by giving us a hypothesis to test in biology that we wouldn't have thought of. So, of course, in reality, we were then panicked, being the biologist, and we should know this already. We said, well, what do tails do? Well, we know that tails store fat, for example. We know that you can grab onto things with them. And perhaps it's most well known that they provide static balance. They can also act as a counterbalance. So watch this kangaroo. See that tail? It's incredible. Mark Rapert built a Uniroot hopping robot, and it was unstable without its tail. Now, mostly tails limit maneuverability, like this human inside this dinosaur suit. My colleagues actually went on to test this limitation by increasing the moment of inertia of a student, so they had a tail, and running them through an obstacle course, and found a decrement in performance, like you'd predict. But of course, this is a passive tail, and you can also have active tails. And when I went back to research this, I realized that one of the great TED moments in the past from Nathan, we talked about an active tail.
Myhrvold thinks tail-cracking dinosaurs were interested in love, not war.
He talked about the tail being a whip for communication. It can also be used in defense. Pretty powerful. So we then went back and looked at the animal, and we ran it up a surface, but this time what we did is we put a slippery patch that you see in yellow there. And watch on the right what the animal is doing with its tail when it slips. This is slowed down 10 times. So here's normal speed, and watch it now slip, and see what it does with its tail. It has an active tail that functions as a fifth leg, and it contributes to stability. If you make it slip a huge amount, this is what we discovered. This is incredible. The engineers had a really good idea. And then, of course, we wondered, okay, they have an active tail, but let's picture them. They're climbing up a wall, now imagine, or a tree, and then they get to the top, and let's say there's some leaves there. And what would happen if they climbed on the underside of that leaf and there was some wind, or we shook it? And so we did that experiment that you see here, and this is what we discovered. Now that's real time, you can't see anything, but there it is slowed down. What we discovered was the world's fastest air writing response. For those of you who remember your physics, it's a zero angular momentum writing response. But it's like a cat. You know, falling cats do this, they twist their bodies, but geckos do it better, and they do it with their tail. So they do it with this active tail as they swing around, and then they always land in the sort of Superman skydiving posture. Okay, now we wondered if we were right, we should be able to test this in a physical model, in a robot. So for TED, we actually built a robot over there, a prototype, with the tail, and we're going to attempt the first air writing response in a tail with a robot. If we could have the lights on it. Okay, there it goes. And show the video. There it is. And it works just like it does in the animal. So all you need is a swing of the tail to right yourself. Now, of course, we were normally frightened because the animal has no gliding adaptation, so we thought, oh, that's okay, we'll put it in a vertical wind tunnel. We'll blow the air up, we'll give it a landing target, a tree trunk, just outside the plexiglass enclosure, and see what it does. So we did, and here's what it does. So the wind's coming from the bottom, so slowed down 10 times. It does an equilibrium glide, highly controlled. This is sort of incredible, but actually it's quite beautiful when you take a picture of it. And it's better than that. It just doesn't just glide, it maneuvers in midair. And the way it does it is it takes its tail and it swings it one way to yaw left, and it swings its other way to yaw right. So it can maneuver this way. And then, we had to film this several times to believe this, it also does this. Watch this. It oscillates its tail up and down like a dolphin. It can actually swim through the air. But watch its front legs. Can you see what they're doing? What does that mean for the origin of flapping flight? Maybe it's evolved from coming down from trees and trying to control a glide. Stay tuned for that. So then we wondered, could they actually maneuver with this? So there's the landing target. Could they steer towards it with these capabilities? Here it is in the wind tunnel. And certainly looks like it. You can see it even better from down on top. Watch the animal. Definitely moving towards the landing target. Watch the whip of its tail as it does it. Look at that. It's unbelievable. So now we were really confused because there's no reports of it gliding, so we went, oh my we have to go to the field and see if it actually does this. Completely opposite the way you'd see it on a nature film, of course. So we wondered, do they actually glide in nature? Well, we went to the forests of Singapore in Southeast Asia. And the next video you see is the first time we've showed this. It's the actual video, not staged, a real research video, of an animal gliding down. There's a red trajectory line. Look at the end to see the animal. But then as it gets close to the tree, look at the close-up and see if you can see it land. So there it comes down. There's a gecko at the end of that trajectory line. See it there? There. Watch it come down. Now watch up there, and you can see the landing. Do you see it hit? It actually uses its tail, too, just like we saw in the lab. So now we can continue this mutualism by suggesting that they can make an active tail. And here's the first active tail in the robot, made by Boston Dynamics. So to conclude, I think we need to build biomutualisms like I showed that will increase the pace of basic discovery and their application. To do this, though, we need to redesign education in a major way to balance depth with interdisciplinary communication and explicitly train people how to contribute to and benefit from other disciplines. And of course, you need the organisms and the environment to do it. That is, whether you care about security, search and rescue, or health, we must preserve nature designs. Otherwise, these secrets will be lost forever. And from what I heard from our new president, I'm very optimistic. Thank you.